Beautiful. So this is Grace, not Grady Payne, by the way. I'm logged in on his computer, but it's going to say that Grady Payne is talking. How are we doing? I already asked that, but how are we doing in the class?
Yeah, I don't recall, yeah, on homework, we haven't done that anything about failures really. Like I think someone would just the RL or the. Yeah, no basis in homework. Also, we're probably not gonna cover op amp at all. And you're still doing second order differentials. Like a smaller question, and also what's rise time?
We will get there. We will get there. Here, we'll get there when we start first order, okay? So, number one, I have not ever heard of the last time he went over op amps, so you're not that far behind. The past couple semesters, it's been 50-50 if you've gotten to second order, so you're not that bad. I mean, I don't remember what textbook he has, but really just online resources about op amps are pretty good, but you'll go into op amps more in electronics. And then circuits too as well. Yeah. So I don't know why y'all haven't done complex admittance. That usually comes before switches, but that's okay. Right. That's what I meant. Sorry. The homework usually comes before the switch problems. The homework with complex admittance. But it's fine. Like I said, did you happen to email? Okay. If someone can shoot him an email just saying, hey, can we get problem set whatever you're on, just so we can have some practice problems for the exam, he'll probably send it out.
I assume it's just name and age of which calculator, like with.
Correct.
Complex numbers.
Yeah. And we're gonna go over that. We're gonna go over it today. It's gonna be cool. It's okay, but we are going to go ahead and start. So for exam 2, this is what I've been told. I emailed Russell and he didn't respond, so I'm going off what he told y'all in class. You're going to have a Thevenin's / Norton's, right? Oh, Jesus. Sorry. There's no way. Like, they've had 3 questions on exams before.
Okay.
That is very, very common, so. Yeah. And then we have complex. Just wanted. But I don't know how to spell, and that is reoccurring theme. But what is the difference? So I'll go ahead and ask, what's the difference between Thevenin's and Norton's in how you solve it? How you solve it.
Therefore, Thevenin name or a one voltage source. That's the most popular.
So that's the big difference. For one, you use name, and the other you use MAME. So Thevenin's, you're looking for a voltage source, right? You want a voltage source. Do you solve for voltages in MAME or NAME?
Name.
So you're going to use NAME. For Norton's, you are looking for a current source. And so you use MAME. Thank you. So it's not too bad. Also online, if you have anything to say, raise your hand because I have it muted. Which of these do we want to start with? Okay. We got Norton in the chat too. I like it. So I have, what do I have? I think I got one. Did I get one of both? Wait, you want Norton's? Okay.
I mean, we're gonna do both, right? Yeah.
So what's probably going to happen is, don't quote me on this, what's probably going to happen is you're going to use MAME for this and then NAME for the other, or vice versa. You'll use NAME on this and MAME for that. So you'll do NAME once and MAME once, probably. So know how to do both. And otherwise, they're pretty interchangeable. It's just for Thevenins and Nortons, you do an extra step at the end. So I have a decent Norton's problem, but we'll go ahead.
Do like the matrix equation twice, like one for finding.
Yeah, it's just the extra step at the end. It's an extra step. It's not bad. So here's your problem. And I want that to go away. I will let y'all take a picture of this and I'm going to read the question. Please always read the question. That gets so many people. So the scaled resistive network contains a current controlled voltage source and a voltage controlled voltage source. Not insanely important. The network is driven by a 16-volt voltage source. Obtain the Norton's equivalent at terminals A, B of the network shown in figure 1. Express Jn and Gn in numerical form. So we immediately see Norton's, right? There are things we should immediately think of, okay? What are the things that we should think of whenever we see Norton's?
Where are these?
Let's back up, but you're close. So whenever you see Norton's, we're going to think of what we said earlier, right? We think of MAME. That?
Oh,
Mhm.
okay.
It's just pretty small, but it's not bad. The exposure is getting annoying. I don't want it on auto. I messed it. Yeah, I'm having a great day, y'all. Okay, so we think MAME. That's where I was going. Whenever we think MAME, what do we think of? Do we think of voltage sources or current sources? We want voltage sources, right? Sources. You can kind of see that. And then we are solving for mesh currents. Solving for mesh currents, and all of our values should be in resistance. All of our resistors should be in terms of resistance. This is killing. Okay. Okay. So let's start. Unfortunately, on this one, he does not give you the arrows. He normally does, but not always. So what he usually does is he goes left to right, and we always go clockwise. Over here, this is what you were saying earlier. At terminals A and B, we need to put a element here. We either put a voltage source or a current source. It's MAME, so what do we put here? We put a voltage source. Do we want it to be facing up or down? It doesn't matter, but. Okay, sweet. I'll show you what happens if you put it facing down at the end. Sort of. But what are we setting it to? 1 volt. And again, I'll show you why in the math later. Exactly why. So now we have IM1, 1, 2, and 3. Are we good with the meshes being labeled that? Cool. As for solving, how do y'all feel about writing out the passive matrices? We did that on the last review, right? For the people who were here. Yeah. Okay, cool. I'm gonna go a little quicker then on the passive matrices. If you want some more in-depth explanation, go watch the other review because I go pretty in-depth on it. And then I'll focus more on the Thevenin and the Norton side and then on the complex numbers side. Fair? Cool. So our passive resistive matrix. What do we got for the first element? 6, I dig it. And then second one, -1. 1 is shared, and remember all of our off diagonals are always negative. And then what's shared between 1 and 3? Nothing. And then just a reminder, we copy that immediately back down because 2 and 1 share the exact same. So now what's the total resistance of mesh 2? Four. There we go. And then shared between 2 and 3? -2, -2. And then what about 3? Just 2. Perfect. And then we have our IM1, IM2, IM3. Have you gotten in your silly little fake? That's on the other side, right? So this is your left side of the equation. And now we're gonna write our equal sign. And we're gonna write our voltage rises over here. So in your silly little math class, have you gotten to matrices and the linear algebra stuff now and matrix multiplication? Ish? Sweet. That is fantastic. And I'm writing this as voltage rises because it's the opposite of passive sign convention. We moved over our negative rises to the other side. And so now if you see it's a positive voltage rise, we write it as a positive value here. For an example, as an example, we look at this first mesh, right? Let's look at the 16 volts first. It's coming in this way. Is that a rise or a drop? And so if we were doing passive sign convention, we would say it's negative, but because it's on this side of the equal sign, we're gonna say it's 16 positive. And that is just a normal number. And what we're gonna do here is we're going to write out all of the sources and then we're gonna separate them out. Cool? And we're gonna call this E naught. If you want to try to squeeze in over there or go on the other side, I don't think your visibility there is great. Yeah. So let's keep writing on the first loop. So what else do we have? We have 16 plus or minus 5 RMI5. That minus mu V4. Sweet. Now what about in the second mesh? Perfect. And then in the last one, so exactly. We are going to call it E naught for right now. I can't remember if that's the notation, if he uses, if it's E naught or not. Thank you. Good call. Good catch. So from here, we're going to separate this all out. We're going to separate it out into independent mesh, dependent plus dependent plus, I always call it a knot. Huh? That's not very helpful, but it's our like E naught. But in my head, I always say it's the knot matrix. But how do y'all feel about separating it out here? Exactly. So if it's a whole number, then it's independent. So what independent sources do we have? 16. Anything else?
We have our own.
Yeah. Yeah, that's our knot matrix. Because this is going to sometimes be on and sometimes be off. And so we're putting it into its own matrix. So then what dependent sources do we have? This mu V4. Perfect. What else? 4, 0 plus 0, 0, negative E naught. Just everything else. Perfect. So first part done. So, and you can do, this is the order I usually do stuff. So next what I do is I write equations for I5 and V4, but you can do this in a different order. It's not a bad idea to write your equations first. So I'll point them out if it is a little hard to see. This right here is V4. And then this current here is I5. I think that's slightly better. How do we want to write the equations? What variable do we want to use for these equations? Mm-hmm.
So I5 would be I2 minus I3.
Mm-hmm.
And V4 would be R4 I2, I think.
Yes, and we'll take a step back and go through that a little slower. These are our variables, right? We want everything in terms of these so we can solve for those. So exactly what he said. If you are solving for current, it's easier to find the current equation. If you're solving for voltage, it's easier to find the voltage equation. So we'll start with current. I5 is equal to, and we want, it's going to be the sum of all of the currents through that branch. So, as you said, what are the currents going through that branch? Now, how do we know if it's positive or negative? So if it's flowing the same direction, it's going to be positive, right? So it's going to be positive IM2, and then it's going the opposite direction, right? So it's going to be IM2 minus IM3. Good. Perfect. IM2, 3. Now let's do V4. So biggest thing, I would see it all the time. If you are writing an equation for voltage, make sure it equals voltage. Don't say that current is equal to voltage. It's not. So how do we get voltage from current? Times the resistance. So we are going to do the exact same thing, find the current in that branch and multiply it by the resistor. So this is, in this instance, 1. So it does end up being IM2, but it's 1 times IM2, right? Everybody see that? Yes? Okay, cool. Sorry. Quiet sometimes means I have no idea what you're talking about. So let's go ahead. We're going to separate this out. So do you mind if I go ahead and do it to the 3x3 and then the IMs, or do you want me to write it out? So the other thing is, where's our IM in here? So here's our, what's up? Can you go ahead and type it in the chat? Because I don't think I have sound on. Okay, yes, I can totally do that. So he's asking if it was over a resistor with 2 currents, right? You would do the exact same thing as you would here. You would, what? You would figure out the sum of the total currents in this. And then multiply it by the resistance. And we know the direction. This is hypothetical. The arrow always points from positive to negative. So that's how we would see if it's the same direction. We would say, okay, going in this direction, that's positive IM1 minus IM2 times R3, which is 1 ohm. I just wrote over. Does that make sense?
Yeah.
Sweet. Love to see. Just erase that real quick. So let's go ahead and write this out. Rm is equal to 2. And so we have 2 times I5. So we have 2 times IM2 minus IM3 minus mu, which is 5, times IM2. And then we just have mu V4, so then we have 5 times IM2 and 0. And then from here, we're going to write it out to where we want this side to look the exact same as this side. So we want it, if we're subtracting matrices, it has to be the same size, multiplied by the same thing, right? So we want to turn this into that, which we can do pretty easily because we have the exact same variables as over there. So we can turn it into a 3 by 3 with pretty real numbers times IM1, IM2, and IM3. We do this because matrix multiplication, that's a little iffy. Matrix multiplication says that this IM1 goes to this column, right? And then this goes here. So we say for loop 1, how many IM1s are there in the first row? You see that sort of? There's none. How many IM2s? -3. You have 2 minus 5. You have -3. And then what about IM3? And then on the second row, what do we have? We just have 5 IM2. So it's going to be 0, 5, and 0, right? 0, and then do we have anything on the last row?
No.
We love zeros. And then we, of course, still have plus our 0, 0, not, and our lonely little 16. What we want to do from here, we want to take this and subtract it over. Haircut doing. I didn't give myself any room. Oh yeah. Subtract. So make sure you keep your signs right, right? So what's 6 minus 0? 6. -1 minus -3. 2, and then 0 minus -2. Mm-hmm. 2, and -1. What's 4 minus 5? -1, -2, 0, -2, 2. I am. And that's going to be equal to 16 plus E naught. Okay. Here's where it gets interesting. Hoping that'll work. So for Thevenins, there's 2 things we're going to solve. We have to solve for Jn and we have to solve for Gn, right? hypothetically, not hypothetically, to, to solve for Jn, we're gonna solve it like normal with E naught equal to 0. So for Jn, solve with E not equal to 0. And then what we're gonna do for Gn, solve with the independent equal to 0. So what we do here is first we turn off our E naught. Oh, now I regret flipping it over. We turn this off because we're looking for the voltage, current, from A to B, right? What's a 0-volt voltage source? A short circuit, so it's just a wire. So with us turning this off, we essentially just made a wire. And if we find IM3, we found the current going from A to B. Now, whenever we solve here, when we're looking for Gn, what is the equation for conductance? Now, what's the equation for R? So can we say that that is equal to current over voltage? Do we agree?
Yeah.
So right here, we are solving for current, right? So we know this. And then what did we set E naught equal to? So now we're just taking the current that we solved for and dividing it by 1 to get our conductance. So we have this as IM3 over 1. And I'm putting IM3, it's not always IM3, it's the current from your terminals, right? So this is how we're going to do it. Let's actually do it. So we have this first. I don't really want to write out the whole thing again. So in our calculator, does everybody know how to solve matrices on the TI Inspire? Think so? Okay, I'm gonna do it with y'all. Oh geez, that's terrible. Yeah, it was working earlier too. Does Inspire do matrix? Yes, it does, which is why it's lovely and I recommend that everybody get it. So I'm gonna go ahead. Oh, this is too bright. Okay. There we go. Technology. Technology. If you wanted to know how to do that, these little guys, yeah, those are brightness. So if you wanted, you can do control less bright, control bright. Fun fact of the day, I didn't know that until like this past year. Yes, that's a good one. So it's a bit of a balancing act, but I'm just gonna go ahead and do this real quick. And do our matrix. We have, oh, no. 4. So, it's easier to solve for J first. I consider. So we're doing it with the independent, which is 16. That's how I do it. Also, if you want to rent one, you can go over and grab one if you want to get practice with doing it. No pressure. Again, I went super into depth on just how to do matrix operations on the first one, so I'll let y'all go look at that, and then I'll go into polar in more depth on this one. So, of these, which is the current? The same thing. So, Jn equal to negative 1.1428 amps. Now for Gn. And remember, you can just arrow up and hit enter, and then you don't have to type the whole thing in again. And so now we're going to do -1 and 0. So now we see that we have negative 1.428, right? Negative. Go away. Why is it negative? But we're dividing it by the voltage, right? We said our voltage was equal to -1. Yes, but here we said in the circuit it's negative. And so here we're supposed to divide by -1. And that is how we end up with positive 142.857 millisiemens. How do we feel about that? It's not too bad. This is the only step you have to do. It just looks scarier.
It's a RRE. You just type it out.
So it's in the menu. It's menu 7 matrix and vectors, and then 5 row reduced echelon form.
Oh.
Yes. So you just literally arrow up and then hit enter. That's always what I do because I always forget the exact menu thing, but that's where you find it. It just depends on the person because it's not a QWERTY keyboard. But this is this. We feel good otherwise about Thevenins and Nortons. The only difference between Thevenins and Nortons is this becomes ETH, and this becomes RTH. Oh, you got different values? What do you got?
So for that, you just have to most of the time. Sometimes it's weird and decide to do the function again for no apparent reason, but most of the time they'll make you a correction in decimal form. For some reason, it just likes fractions. Um. I think I match for the first, for the JM. Let's say, look at the JM. Yeah, matches for that, and then the GM. Oh, can we, just one more time, go over what we did after we did the first inverse matrix, like that one where.
Say that
Oh,
again?
sorry, no.
No.
So that, you're hovering over in the calculator right there, what did we do after we did the inverse of that matrix?
So you're saying to solve it like the typical where you do the inverse times the vector?
Yeah.
Okay, so the other way to do it without doing the row reduced echelon form is you do a typical 3x3. You raise it to the -1, and then you multiply by a 3x1.
On that one.
Exact same. That's more buttons to
Yeah.
press. And I like pressing the least amount of buttons. But that is exactly how you do it. And I will prove it to you real quick. Mhm. Yeah, nope. We'll do 16. Oh. That's user error. That's better. Exact same. Yes. So we come back to our circuit. And we said that we want the voltage from A to, or the current from A to B, right? Which mesh is that? And so that we're looking in the answer for IM3. If for some reason, and this is not unheard of, he put A to B in the middle of the circuit, you would just say it's 1 minus 2. You would just figure out the current in the equation and then solve for that here. Cool. While I have this all set up for the calculator, I'm going to quickly go through how to put polar numbers in the calculator, which is like, excuse me, the biggest thing for this test. So you'll kind of see that. That's better. Okay. So there's a couple things we need to know whenever we go into no, I actually don't, it doesn't go down anymore. I am on the low, it's very dark up here. So I just want to help you see this thing. So I turned up the exposure a little, and then when we go back to the super in-depth matrices. So we need a couple things to make sure that they are correct. So we're going to go to the document settings. You can also get that from the main menu. So document settings, and then document settings. So this is where we change, and this is how I get to that exponential format. So it shows everything in factors of 3. So it did 10 to the -3, which is milli. But the important thing is that you have this in degree, because everything in this class you will do in degrees, because of how the sinusoid functions work. And then that's not what I wanted at all. Real or complex, best to keep it in rectangular. For the calculation mode, approximate, if you put it in approximate, it always gives you decimals, which is nice. It very rarely can give you a little bit of error and funkiness, but it's not a bad idea to put it in approximate. And then you're going to keep it on rectangular, which everyone should have theirs in rectangular already.
Where's the one there?
Huh?
Okay.
Okay. So then,
Only because we-
yes, there's two ways to get to it: document, and then settings, which is 7, and then document settings. You can also get there from the main menu and just go to settings. Exact same thing. Yeah. And that's a different page, but it's okay. So from here, there's two methods to get it in the polar stuff. So this pi symbol down here, y'all should know that because that's how you get to your pi. But you can see up here, you have your I. So the letter I on the keyboard is not your imaginary number. You have to use this funky bold I, or otherwise it will not work. I have seen people set the letter I equal to the imaginary I, and then they can just put I everywhere, which is smart. I haven't done that personally, but you definitely can do that if that is easy for you. So to set something equal to each other, use this colon with the equal sign. And then you put in your variable, like if I wanted to say that J is a bad example. If I want S to be equal to 17, I would do S and then the little thingy and then 17. And now anytime I say S, so if I do S times 16, bless you, you're good. S times 16 is now 272. So very helpful, especially in EMAG. The little so and immediately regret doing that because I'm showing you the other way to get so I found this out recently. You can either go to the book or you can actually do control book. So literally the thing that looks like a book over there. You can do control that, and then you're prompted with this big screen of things. And you're going to want to use the polar symbol. And that's how you're going to input polar numbers. The one thing that you have to remember is that it does not like it if there's not a parentheses. So if you want a polar number and you wanted to do 10 phase angle of 65, just make sure it's in parentheses. Right now I have it set to give me rectangular numbers, but that's in that document settings where you can actually have it here, and I'll just prove it to you. Well, then it would just spit back out. So if I put it in real or complex mode, and then I put in this guy, I get that. So you can do that in the settings, or what you can do, if I wanted to say, okay, I want this to go to rectangular mode. The helpful thing is in menu, under number, because it's a complex number, there's complex number tools. So from here, you can do complex conjugate. You can say the real part, which you shouldn't really need to do a calculator for. The imaginary part, polar angle magnitude, or convert to polar and convert to rectangular. So that's how you're going to say.
Menu to
Complex number tools.
You're saying like if we solve the matrix and we can do convert the rectangular or polar,
So I'm saying the answer, I want it in rectangular form. It gives me rectangular form. It's fantastic. You do not have to do all of the gross math. The gross math is not fun. So your menu number, because they're complex numbers and complex number tools. Yeah. So from here, let's actually do a problem with these. I have to completely go full setup, which is fine. We're going to do this. It was the top page of paper. So dang it, it's another main. Do I have a name complex mittens problem? That would be super helpful. I do. So just so we get some practice with name in, we'll do this. So let's read it. The network shown in figure 2 represents a scaled RLC network with 0 initial conditions. That just means you don't have to solve for the homogeneous part. The complete solution. I get them mixed up. The source connected to terminals A, B is an AC current generator. It is JG is equal to 10 cosine 4t. It wants you to generate the sinusoidal steady state expression for AB. Where is AB? AB. In the time domain format of a voltage times cosine times 4t plus phi, where this is the magnitude and that's the phase angle. It just looks more complicated. So whenever we yes.
Oh, this is that. Yeah.
This is that.
It would look familiar. Oh.
It's really not bad. I promise. It's the exact same. So let's go ahead and convert this. We don't want a cosine in our matrix, right? So what we're going to do is we're going to change it into polar format because that's the easiest to extract, right? All a polar number is from a cosine or sine is it's going to be A, B. So where I'm actually going to do it down here because this is easiest, where this is amplitude and that's phase angle. That just comes up here. And so this, that's the amplitude, right? What's the phase angle? 0. So what's JG? It is just equal to 10. There's no plus here. So this is omega t, right? So from here, and this was my next question. What is omega here?
4.
So JG is equal to T, omega is equal to 4. And that is just inherent. And he already told you this here, but omega never changes. Omega will never, ever change. If he gives you that it's 4T up here, it will be 4T down there. Don't have to worry about it. The reason that we need omega is for calculating the impedance or admittance on here. So let's see, what's our first step? What do we want to do first?
All capacitors, inductors, complex.
I like that. So I'm gonna write out the same thing that I wrote for the other one, because we see that this is name, right? Do we see that this is name? No, he didn't tell you that. I'll tell you why I know it's name. He gives us VN1 and VN2. If he gives you nodes, it means he wants you to use name.
He gave us nodes for main problems in the homework. I distinctly remember this.
Well, did he give you both? If he gives you nodes and no mesh currents, it's going to be name. But the other two clues, he only gives you current sources, right? Because we see that this is name. And we think current sources. And then we think conductance. What is conductance in complex? So resistance. Sorry, what is complex resistance? Let's do that. Okay, cool. So do we know what 1 over impedance is? Yes. So complex conductance is admittance. Which is Y. So whenever we see name, we think admittance or conductance. We think both. And the other thing we think of is, no, I think that's wrong. Why am I blinking on the other thing? Oh, node voltages. Node volt.
Don't both ever have a different phase from each other.
Because we're putting everything into polar, it doesn't matter. Like, we're gonna solve for it. So let's go ahead. Oh, and the other two clues I was going to tell you about, you see how these are already conductances? It's another good clue. And then, yeah. So now let's write out, well, no. Let's write out all of our admittances. Do we remember what the equations for impedance and admittance are for capacitors and inductors?
W times L for inductors. That'd be impedance. And then capacitor would be 1 over WC. And I assume that admittance would be the reciprocal of those.
Mm-hmm. I got an order. Thank you. I'm really thirsty. I've been talking for a while. But exactly. So, well, almost. So that is our reactance. The thing that makes it impedance is the J. So sorry. That's so rude of me. Also, there's a materials on this where Russell says all of this. I highly recommend having that pulled up, or just write it down on a cheat sheet. So I'll go ahead, say it. Yeah. So for an inductor, so for L, Z is equal to J omega L, Y is equal to 1 over J omega L. This is going to be the easier way to put it in the calculator, because that's an easy formula where you literally just have omega, which is 4, and then your L. So you can just do 1 over 4 times L instead of doing the whole, you know? And then for capacitor, our Z is equal to 1 over J omega C. Y is equal to J omega C. They're inverses of each other, and then the inverse is inverse of the impedance. Inverse. Well, that's interesting. Okay.
It's the same recording though, yeah.
Yeah. It stayed recording. Cool. I don't know what just happened there.
So for L, Y equals 1 over J over L, right?
Yeah.
Okay.
It is amazing and a curse and terrible at the same time. So let's go ahead and write out. So for C1, what we can do is, since these are labeled 1, 2, 3, 4, we can say Y1, Y2, Y3, and Y4. Well, I'm not grading anymore, but I've also seen people do Y, C1, Y, G2, etc. I texted 2 people and then they both brought a different Dr. Pepper. So we'll just do that. So what is YC1? Two F, and then our Y is J omega C. So it's going to be, what was our omega again? So it's going to be 8J, right? So we have 8J. What about G2? Trick question. It's 2. Admittance is in Siemens. So this is Siemens, that's Siemens, and that's ohms. So just like impedance is in terms of ohms, admittance is in terms of Siemens. So conductance is already Y. And yeah, this is 2. Y3.
Real quick,
Yes.
like, how do we know which one is like which for Y, for which one?
Sorry, this is C1, so I'm saying that that's Y1. And then G2, sorry.
C1, G2, L3, and then G4.
Yeah.
And then for each of those blocks, yeah.
Yeah, sorry.
All right.
So, um, I don't know the best way. One. Cool. So let's do the inductor now. So it's 500 millihenries. So we're doing 1 over that. So it's going to be, just write it out, 1 over J times 4 times 0.5 is going to equal to, it's 4 times 0.5. So it is going to be 0.5 because it's 1 over 2. So it's going to be negative. And so that's the other thing that I meant to say. That's my bad. So if we're looking at inductor, y is equal to 1 over j omega L, which is also equal to negative j over omega L. I find that annoying personally, because I will sometimes forget the negative there. And then it's also easier to just directly flip it, again, for me, but 1 over j is equal to negative j. That is inherent to imaginary numbers. So these are the exact same thing. I write it that way because visually it's easier. And then you can put it in your calculator and you get that it is, in fact, negative 0.5 j. Then y4 is just equal to 4. How do we feel so far? Great, because that's the only new part. Everything else is the exact same as what we've already done. So let's write our matrix. It's going to be a 2 by 2, right? Okay. So what are all of the impedances or admittances touching node 1? Have y'all gone over name for an exam?
Oh, we didn't do anything.
Okay, let me back up for a second. I'm gonna show y'all how I like teaching.
You have to simplify this circuit by like adding up the resistances now.
No,
We have at least one pair of them in parallel.
no. We don't have to. We're using name. And you don't have to do that for that, which is lovely, right? So how I like doing it is for each node, right? To figure out the conductances is I literally look at, okay, what are all the branches connected to this node? So literally look at this one, this one, this one, and that one. And so make sure that every single branch is what you look at. And then once you hit an element, you stop. So for here, I mean, you could, but especially like if you wanted to separate out and find the currents of them, there's not really a point because even though they're already in conductances, you would just add them,
Oh,
but then you're already just adding them.
oh, right, yeah, I forgot we're conductors, so we just come the parallel. That was like, oh, why do we have to, like, how can we just add those if we have to do like that, like 1 divided by 1 over?
Yeah, so that's why we're in conductances and it doesn't even matter. So for this one, I'll go slower. Are there any conductances on this branch? Sweet. So here, we see up here, we have 2, right? And then here we have negative 0.5 j, and there we have 8 j. So for our first box, first element, we're gonna add those up. So it's gonna be 2 plus 8j minus 0.5j. And then what is shared between node 1 and node 2? Exactly. And can you see that? Can't see that. We're gonna do the same exact thing. We can also do it with highlighters, but this works because I don't have highlighters. But this is more of a visual representation. It's okay. I can do my little. Oh, sweet.
But I'm extra.
No, you're good. This works because then I can erase and do all of that. This is kind of a visual representation and like, okay, I can see that these two are shared. And so it's easier to see that.
How many nodes are there again? Are there like?
There's two. And he labeled them, right? So he labeled VN1 and VN2. The only other node you have is ground, and we don't count ground as a node for our meshes.
Well, why is it the one at the bottom of the node?
There?
The other one.
So there is only a wire connected there. If there is not an element between 2 points, it is the exact same node. So this whole thing actually is ground. I got out my eraser, but. Ah, there we go. Thank you. Neat. I have erasable colored pencils and they're mechanical pencils. Really cool. So that's technically this is our and by. Thank you. There we go. Good stuff. Now we're good. So this is n by n minus 1. Okay. So what's shared between 1 and 2? We already said 2. So it's going to be minus 2 minus 0.5j. So I did minus on the outside, so it's actually going to be -2 plus 0.5. Yep. Yep, it's a tricky one. And then what is all of the ones on 3? I'm just going to go ahead and say 6 minus 0.5j. Times 1, 2. So now let's do all of our current rises. So what do we have for the first line? First mesh, not mesh, geez, node. Exactly. And what did we say JG was? Just 10. Up here, we just have 10. Perfect. Yay. Now, we have beta I1 on the other one, right? Is it positive or negative? Oh, I meant to say that for the other one. Is it positive or negative? Why? And I always found this easier because if it's entering the node, it's gaining the current. If it's leaving the node, it's losing current. So entering positive.
That does make.
Right? The mesh one is harder in my opinion, but people always have a hard time with name. Name just looks scary. But so same thing over here, right? It's positive. Yeah. Yeah, that's fair. So, but we have beta I1. Look, it's pretty small. So I1. How do we find I1? We're going to use our node voltages. So same thing. This is our variable. How do we write current in terms of node voltage? Just what's the equation for I? Over I. So what does that also equal to? B times 1 over R VG. I wrote out a lot of extra steps. That's me just saying I is equal to VG. You don't have to write all of that. That is just the linear progression of how you get there. Does that make sense to everyone? Sweet. So we have the voltage here, and we have a conductance over there. So we can find our equation pretty easily, right? What is the voltage over it? So the voltage over an element is equal to the difference from the starting and the end point, right? Okay, so what's the starting voltage? And I say starting because current flows from high to low. Perfect. So if it's flowing from a node, that's the high node. So what's the starting point? What's the ending point? So just yay. So I1 is equal to VN1 times RG, which is 8J. Right? And then times, so then this whole thing, well, I guess we'll plug this in here. We're going to do the same thing of separating it out, 10 and 0 plus 0, and then beta right here is 2 plus 3J. 2 plus 3J times 8J VN1. Kind of long, but now we do the exact same thing. I'm just going to do it quickly because it's kind of a bit annoying. I'm going to 2 plus 3J times 8J and 0. Cool with what I just did? Exactly. That is exactly. So he said, what if we were doing from VN1 to VN2 over L3 or the other one? It would honestly be easier to do the 1 over G2 just because you don't have to multiply by a complex number. But you can do either because voltage is the same in parallel, right? So you would just do, if the arrow was going this way, it would be VN1 minus VN2, because it's flowing from high to low, times exactly what you said. Oh, no, you said divide. So that's where the VG comes in. Since we solved for conductance, that's in Siemens, we would multiply it, not divide it. Does that make sense? See. Increase that, but that gets confusing. So does this make sense to everybody? Cool. We're gonna subtract it over. The reason I wrote this out is because what is a j times j? -1. Physics 2 was a while ago for some of us, right? I know some of y'all are taking it concurrently, and then there's people who took it forever ago. It's a fun batch. So you just got to be careful because this ends up being 16j minus 24. If you are shaky doing that, do it in the calculator. It will do it all for you and be right more than us probably. Yes, exactly. Sorry, I should have said that sooner. Electrical engineers use I as current, and so they said, we don't want to use I, we're going to use J.
Someone else agrees.
Oh.
But are obviously secure your notation.
So we can go ahead and write this out. So this is going to be 2 plus 7.5j, 7.5, and then -2 plus 0.5. -2 minus 24, going to be 22. And then plus 5 minus 16, -15.5j. And then 6 minus 0.5. There. And go to 0. All right, my numbers started getting a little sloppy. But from here, we do the exact same thing of we put it in the calculator. Go ahead and do that. 3. And do that, we're going to do the 2 plus 0.5, and then we get that I. Care more about seeing the screen or the buttons? It's a little happy medium, hopefully. So -2 plus 0.5j, then we have 10. And since it's just 10, even though it is a polar number, we can just say 10. 2 minus 15.5j. Oh, and then some people have also plugged in for j that it equal to I, and so they can actually say j. Just whatever makes sense in your head. Graders do not get access to your calculator. I didn't do RR yet. Okay. So see if you get the same as me.
Oh, I did something. I actually know.
It's also very possible that I did something wrong.
Did put my polar had to convert.
Do you remember how to convert to polar?
Yeah, it's number
2.9, other way around, but yeah.
Yeah. 296.
And luckily you can do, so if I wanted to convert it to rectangular, it'll do the whole matrix for you. You don't have to do the numbers by themselves, which is lovely. The reason I have it set to, I kind of want it to press the zoom button, but then also it's probably gonna get all unhappy with me. The reason I have it in polar is because we have to write our end answer in cosine, right? And so if you put it in polar, you just extract that out. Yes, exactly. Well, sort of. Almost. You also have to have the omega t. So this is our answer. So it's asking for VAB. Where is VAB? There, right? So from our matrix, what is VAB equal to? Is it VN1 or VN2? Or both? Because this whole thing is the same. Well, it's saying that A is positive and B is negative. That's the same as this polarity, right? So it's not going to be negative. So our VN1 over here is 1.1599, phase angle negative 6.96. So we're gonna remember we have our phase angle phi. Our VAB is going to be our magnitude, which is 1.15969 cosine, and that 4t, because that never changes within the problem. And then we have negative 6. So we have 4t minus 6.9662 volts. Please write your units. Especially if you have it all in millivolts, make sure you write millivolts at the end. Very important. Yes. Wait, sort of. We're doing the top one because that's A, B. Okay. Yeah, if it asked for the voltage over here, then we would do the second VN2. We would do VN2, not VN1.
Same frequency, but
It's the exact same. You're just looking at the answer. So even if there was another independent source here, you would still get the same, you would just get another answer.
oh, but if we had different ones, different.
You can't really do that within a circuit because the frequencies are going to collide and then change, right? Correct. And so they're not going to stay at the frequencies. And this is at such a small scale that we're looking at that the wavelengths are not, they're much bigger than the size of the circuit. Basically, you can't do that. Fair enough?
Can I see how you put the matrix in the calculator? And what the changes?
So you're gonna do the same thing. I get my matrix from this button. this button. Then get my matrix. And then you literally are just doing that pi and the I sign. So if I wanted 15, you just do 20 I. 30 I. 3, 9, 2, 5, 3. See though?
Are you putting right whenever? Oh, I think that's how you do the imaginary in the calculator, but we wrote it J that. That's how it like then they come over.
Mm-hmm.
Yeah. How'd you make it do the angle again? Like
So in my calculator, in my document settings, right? I currently have it set to polar.
or the other way you could do like something.
Yes. So you do menu to number, complex number tools, 9, convert to polar. Yeah. Also, I don't know if you know this, you can hit the numbers instead of going down.
Oh, I didn't know.
Yeah. So you can just hit 6 and it just does the 6. It is cool. There's a lot of shortcuts. Also, thing I didn't know recently, you can do copy and paste with Control C and Control V. Oh, and you can undo too, but you can Control Z.
That's kind of like control right here. I've been trying to highlight it in like scroll thing.
Ugh, that doesn't sound fun.
It's not.
Okay, do you have any other complex questions? Okay, it is the exact same. There's just fake numbers in it. Cool. So let's do the switch problem, which is the hardest one. But obviously, you know this. They're imaginary. They're not real. I tell all of my non-EE friends, I'm like, yeah, electrical engineering is fake. It's not real. It's all not real numbers. Yep. But that's because I'm a nerd and nerdy. So, oh, wait. No, I don't want to do this problem. This problem is a pain. And so,
Sound like that one limited view. Like the circuit, it still has the same symbol.
yes, it's because the circuit is really annoying.
You should probably do that.
We're not gonna start there. We're gonna start on the easy one. And then if there's time, we can go in, but this is gonna be a really long review anyway.
It's like 5.
Yes. But you can definitely, if you want a picture of it and you want to do it later, you can also do that. The reason why it's weird is it asks you for the current and you end up getting a voltage source and a current source in the same circuit where you can't transform either of them. And so you have to do some funky stuff, and superposition is the easiest way to do it, but you don't really go into that a lot. And so it's just harder and there's more complicated things. And I would like to focus on how to do the switch problem first and then go on to the other stuff. Did I? No, I did not either, because 95% of the time you don't have to use it. It's just if he decides to randomly put a problem where that's the easiest way to do it, but then he doesn't teach it, and that's
Be very unlucky if we had to deal with that.
and we can go over it at the end. It's not hard. It's just not something that you do normally in this class. But switch, yay. RC network in figure 3 has been at rest for a long period of time with switch 1 closed. At time 0, switch is opened as indicated. Using the values, you are asked to do the following. Calculate the values for capacitor voltage, the capacitor current, and the network time constant, tau, and fill out table 3. Apply these values to write the full complete time domain expression found from the solution of the network equation. And for shits and grins, we'll also find the rise time. Just so you know how to do it, because sometimes he'll ask. So, have y'all seen this table before?
Yeah.
Great. He didn't teach it last year for some reason. I don't know why. So that's fantastic. If the thing doesn't have the table on the test, I recommend still drawing it. I think your homework questions didn't really have it most of the time. It's very useful.
Second order, we get like extra, like we showed our work points.
I don't grade anymore. What I would do is if you write, and I can't promise that they're going to do this, but we know what the capacitor voltage is at 0, at like negative infinity, right? And positive infinity, 0 minus, not negative infinity, geez. What's the capacitor voltage after a long time? Exactly. So we can write 0. And what I would do would be, I would give 1 point for that. I can't promise that he's going to give you 1 point for that.
Oh, so like not worth it, like kind of,
No, well, 1 point is a lot.
not great.
But I would still write it because then you do show, and it just it helps you, in my opinion. But anyway, let's start. Easiest thing is what I just said. After a long time, the capacitor voltage is going to be 0. So we can fill in 0 because 0 minus is after a long time, right? Right before 0 is essentially just it has infinitely been at the previous thing. So 0, and then after a long time, oh my gosh, I'm doing it wrong. Why did nobody stop me? Oh my gosh, the current is, guys, I've been spitting lies. I cannot believe nobody stopped me. I brain farted, excuse me. There is no current that flows through a capacitor after a long time. There is a voltage across it. So yeah, exactly. And that's actually what I was about to say. The easy thing to remember is, for me, I think about what a capacitor is. A capacitor is 2 metal plates, right? What does that kind of look like? Does that look like an open or a short? It looks like it's literally not connected. And so after a long time, it looks like an open. Exactly. It is literally just a coil of wire. I don't know if you've ever, like I got to make inductors at work, and we take this really fat wire and we literally just loop it around, and all of a sudden it's a magical element that we use for everything. And so after a long time, a wire looks like a wire. And so that's how I think of it. And a wire, after a long time, has no voltage across it, right? And so after a long time, an inductor also has no voltage. The only time that these will ever have their other things, right, is as soon as the switch closed. It has its response, because we're just going to look at a capacitor for right now and just know that everything I say, it's the exact opposite for inductors. The exact same, except the exact opposite. Simple, right? Not confusing at all. So this will build up a value here. It will literally build up charges after a long time. And then whenever it switches, a capacitor resists change in voltage. And remember that, right? Resists change in voltage. Because of that, it does not want to instantaneously change. What it can change instantaneously is current. So because the voltage from here to here is the same, the current here, there will be some instantaneous change in current. And so we can only solve for this value once we know our negative infinity value. I don't know if I'm making sense. I feel like I'm rambling. Let's solve the circuit. Yeah.
We solve one case and another one.
So we can't solve for this current value until we know what the voltage is.
Oh.
So what we're going to do is we're going to solve for this voltage at -0. Did you just like do that in your head? Okay, well, we're gonna solve it together. Okay. We're gonna solve for the voltage, and then to solve for the current, we're going to treat the capacitor as a current, as a voltage source, because it resists change in voltage. So we use the voltage here, and we change it to a voltage source on the circuit and solve with that voltage source there. Cool. Yes. Does inductor voltage change instantaneously? Yes. It resists change in current. So it instantaneously changes voltage. Let's do this. So I'm normally not the biggest person for like redrawing every single step. When it comes to switch problems, redraw the circuit 3 times. It makes it a lot easier because the circuit will change so much on these. And when you redraw it, you realize a lot of times how you would actually solve it. Okay. So we're gonna redraw it at time is equal to negative infinity. So that's still gonna exist, right? So -0, geez. This is about the time where it's like, yeah, I've been talking for a long time. My words start not making sense. So what I do is because the capacitor has no voltage current going through it. It behaves as an open circuit. I just draw little terminals. Yes.
That would not exist for the actual case because it's like, right, at t is equal to 0 and negative.
Oh yeah, I drew it wrong. Yep. No. Yeah.
Oh, I see. Start close and then the switch open and at t equals 0. Oh, no.
Mm-hmm. That is still there. So this is gonna be 9 volts. Okay. 8K. 3K. So let's see. We want the voltage from here to here, right? How do we think we want to do that? What do we see here that we can kind of manipulate this? Feel free to spitball.
So manipulate what way?
To write it so that it looks a little cleaner, because it's weird, right? Just having this wire down here. Okay, so you probably had this on your I shift or E shift problems. I'll go ahead and tell you how I would redraw it here. Is this the same?
Yeah, good. Because they're both touching the bottom.
Mm-hmm. Now, do you see how we would find the voltage here? Mm-hmm. Exactly. And this current and that current are not touching. And so we don't even need to do that. We can just do a voltage divider. We can either do a voltage divider or we can find the current. We can do it either way. Does voltage divider or finding the current and finding voltage across that resistor sound better? Do we agree with voltage divider? Like,
Yeah, I think it looks good.
okay, so we have 2K, 8, 3. Nope. 9. So we want this voltage, right? So are we going to find which we're going to find the voltage here, right? Okay. So voltage divider between 9, 2, and 8. So what is that going to be? Ooh, what's that equal to? The gross number. And then the other one is going to be should be 11. It's a
No, it should be 8, 9, 10.
Okay, 8/8 + 2, and then 3/3 + 7.
mm-hmm.
After I thought those were 11, probably won't have it by next week.
9 plus 2. You're is just adding the wrong thing. Uh, so it should be what 7.2 and 5.4. Oh, yeah, that. So that means that here it's going to be 7.2. There it's going to be 5.4. So what do we do now? Do we add them?
Oh, wait.
There we go. So VC of 0 minus equal to, what's that, 2.2? No. 1.8. 1.8. 1.8 volts. We all agree?
I find that table is really.
Exactly. So it's 1.8 volts and then 1.8 volts. What I would always write, and my students last semester started picking up on it, I would literally just always write equal there. And then, so now we can either solve for infinity, or we can take this and go ahead and solve for the current. I agree. Let's solve for the current. So what we're going to do is we're going to take that 1.8 volts, plug it in as a voltage source, and redraw the circuit, unsurprisingly. And we'll see how it looks. Fair? So this switch opens. So now we have 9 volts. Okay. Make sure you get your polarity right. Okay. Bless you. I mean, you could draw it as a diamond, but we're solving it at one point, and so it is independent of time. So now, what does this look like to y'all? To me, this looks like 2 meshes.
One small one in the middle and the big one outside.
Mm-hmm. Big circle. And a 2x2 MAME problem is pretty easy, right? All voltage sources, we love it. So let's do a real quick MAME. So I'm going to call this mesh 1 and this mesh 2. So what's all the resistances in the first one? It's 20, 20K, 20K, and then 11 shared. And then in the other one, it's just 11. Uh, 9 plus 18 is 27. Mm-hmm. They are. You're right.
Be negative on
Yep. Okay, and now we can solve that super easy. Mm-hmm. Nothing dependent, nothing complicated. 3. Type. And what I've always done is I do E3 to do magnitudes. That's the same as times 10 to the 3, but it's just this button instead. Is that little E. It's, I don't know. I have little quirks, I guess.
So can you show them where you find E again on your?
Yeah, it's right above the I button. This little EE.
Oh, okay.
It's especially helpful once you start getting into the like mega or into the nano, because you just do E to the negative to do negative, obviously. Did y'all get this? So which one is it? Hmm. Exactly. Make sure you see it's milliamps. So we're gonna come back up here.
Oh, I know, but I'm getting micro.
Did you make sure to do the K for all of them?
I'll put all of them back out.
Not. 1.3636 milliamps. Now we just have to find that both V is equal to infinity, right? And then tau, and then the other thing.
Is
Yes.
the current is point positive because I see it to be fine. Oh, never mind.
Cool. Yeah. Just make sure you follow the direction here. Because it's very, very plausible that it is the opposite way. So just check yourself. Now all we gotta do, we gotta draw it at infinity, which is the exact same thing here, except there's an open source, open circuit. I will draw out again. If you feel relatively okay, I understand. But the longer I write, the more my resistors look like inductors, and the more my inductors look like resistors. This one's not bad. What do we think we're gonna do here? Yeah, I'm good with that. I would find current and then just add the voltages over those two personally, but voltage divider is also good. Because we all see that that's just one wire, right? Okay, sweet. So actually put in the values, PK, AK, 7K. So what's the essential voltage? Let's just combine those real quick. We agree with this. I did a lot there. Do you want me to?
Oh, yeah, because yeah, we know it's all one wire, but why is the positive and the negative that way?
So what I did is I combined these that way. So 9 minus 18 is going to equal to 9 that way. But then I kept these the same polarity. I also dragged this around. So I knew that it was gonna be 2 and 7, and then in the middle 11K. But that's the same as 2 plus 7 and then 11K. Since it is just one wire, since they are all in series, that is correct.
So the polarity of like plus and minus, they're swapped. Is that like necessary? Not really.
They're not.
They're not. Okay, not. Let me just go over again how you swap them one more time.
Here, I'll not skip steps. I was trying to be lazy. So this is the same, and I think that this will make it a little more clear. Does that make a little more sense?
Yeah.
Okay. All I did is I just took this one and went around the back. That's all I did because it instead of one, it's just two things, but it doesn't really matter. Like I said, I was just skipping steps.
Okay.
Cool. So we have 9. So it's in the opposite direction. So we know it's going to be negative. So it's going to be 9 times 11 over 20. Yeah. Yeah. $4.95. Mm-hmm. Negative 4.95. Okay. Yes. So how do we find tau? What is tau equal to? So how would we find that?
Use the 7 to find the equivalent resistance. Multiply that by capacity.
Mm-hmm. Sort of. Almost. So the only issue with saying find the Thevens, that is true. Oh, sorry. Why is it -9 again? You're good. So we added this voltage source with this voltage source, and this, they're opposite polarities, right? So now this source flipped to -9. The really important thing about finding tau is the terminals are at the capacitor. Because you are looking at the resistance the way the capacitor sees the circuit, right? So you put yourself in the mind, in the place of the capacitor, and then you find resistance. So you do turn off all your sources. So voltage sources become shorts and they become opens. And I am like second guessing myself. I'm trying to make sure that I say the right thing. But I'm trying to make sure that I say if it's before or after the switches.
But doesn't it stay the same for all of them?
Well, the circuit changes.
After the switch?
Yeah, T greater than 0.
Okay. Like I said, I'm like pretty sure, but I was second guessing myself. Yeah. Mm-hmm. Okay. After the switches, so we're gonna come back to this circuit. So I'm gonna say we're gonna come back to this, except we're gonna make these shorts. Right? So, but instead of drawing it like this, well, I guess we can draw it like that, but I'm gonna draw it the exact same. I'll show you. So from the point of this plus and minus, 2, 3. Are these all in series or are they in parallel?
So, let's see,
Which ones are parallel?
so 7 will be series, 8 and 3 will be series, and then those will be parallel.
Exactly. Precisely. Because these are terminals, we cannot add these two in series. We cannot break these nodes. So you can't, nothing is going to be in series. Like you have to pretend like there's something connected here.
I think it's part of the proximity
Mm-hmm.
or parallel.
Mm-hmm. So you can do it also, you can flip that over, right? So you can have this.
You also just write it where it's like there are two nodes sticking out on top.
Mm-hmm. So you can write it like that, or that's in parallel. It's A and B. And you've seen circuits that look like that. Those are in parallel. Mm-hmm. So basically, it's 11 in parallel with 9. So it's 9 in parallel, 11. A gross number is the answer. Huh. That's crazy.
I'm supposed to be below it.
It's just that it's the same that I was just. Oh, it is. Huh. I was just surprised that it was the same as the voltage. That just took me aback. And then what is our actual capacitance? So 27 nanofarads. So then that is times 27e, and nano is negative 9. It's right above the pi. This guy. So
I've just been doing like the times 10 to the painful.
it is. It gets a little funky. So it's 133.65 microseconds.
What's the equation for that?
Tau is equal to RC. or tau is equal to L over R.
Four point nine five multiplied by. What are the parts of the problem again?
It's a great question. So first it tells you to fill in the table, fill out table 3. So now we have adequately filled out table 3. Now it wants us to write the full time domain expression. What is the equation for the time domain expression?
D of infinity.
Mhm.
Plus 50 minus infinity.
Mhm.
Yeah, I think that's it.
Yeah. And write that down. Don't try to memorize it. Write it down, have a cheat sheet on the exam. I still struggle remembering which one's the order today. But V of t is equal to infinity plus, let's see, 0, let's see. Give a tau. Now we have all those values, right? So we literally just plug it in. So what's V of infinity? Plus C of 0, 8 minus, which becomes plus 4.95 e to the negative t over 1 point, no, not 1 point, 133.65 microseconds.
Are we allowed to have our like notebook in the exam?
Yeah.
We didn't have.
What?
We were able to bring this last time.
Oh, I thought you said we weren't able to.
No, we were.
Yeah.
You can use it.
Yeah, don't watch a video. Please don't watch a video during the exam.
And. Oh, like, has that happened? It's like, they're like, the kind of notes.
No, it's literally my video. They've tried to watch this video in the exam, and I'm like, I appreciate that, but you can't do that. So don't do that. Don't ruin it for everybody else, is what I always say. Ruins for like hundreds of people ahead, like behind you. Don't do that. That's not cool. So that's the answer. That is our V of T.
Okay, anything really simplify like the type of.
You probably should.
Yeah, we don't have to draw it, but how to that.
Yeah, you probably should. I just didn't want to do the math in my head. I don't think it's that hard, but
No, it's okay. I don't know if it's not fully simplified minus 1 point.
I hope not. I wouldn't think that's very cool.
I wouldn't think so.
But again, I don't grade. Is there a link to the first review as well? It's on the HKN Teams YouTube channel. It's also on here in recordings in the teams that you are currently on. And then this one will later be uploaded to YouTube. So we asked, what is TR? Time rise. It is the easiest equation in this whole class. It is literally just tau times the ln of 9. That's it. So it's just this guy times ln of 9. That's the answer.
Have you right, literally that, it's not like micro seconds or something.
Hmm?
Oh, if we guess that, like, you put like e to the negative 6, like, whatever, like microseconds.
It's good practice to write micro, but the reason I put my calculator in this is because it gives you like 3, right? So this is E3, that's kilo. That is micro, right? That's why it's nice having it in engineering notation, but you should. You probably won't get counted off, but that's just good engineer notation. It in the habit of doing it, you know? So that's equal to 293.659 microseconds. It didn't ask for that, but that's how you would solve it. And then the other thing it can ask for is the time that voltage is equal to 0. So how would he ask that, T1, where voltage is equal to 0?
All the time too, when both equal to 0.
Yeah, like,
Yep. No, it's exactly. So instead of V of t, you put, okay, 0 is equal to that.
wait, why is it ln of 9?
Because it's the percent from 10% to 90%. It's the time it takes to get from 10% to 90%. And Russell, if you go and ask Russell about it, he'll go on a really, really long rant about did he go on it in class? He was like, this is the thing that ties these two people together.
Well, this Rice time, like one time in our notes, but like kind of forgot.
Yeah,
Like triple weekend.
yeah.
But like I feel figuring it out years like
Mm-hmm.
Time is that important for this?
It's
So it's like between.
yeah.
Like that's not, yeah.
Mm-hmm. And it can tell you by the time that it gets up to 90%. So like on an oscilloscope, right? It would tell you how long it takes to get to 90%, because that's really helpful. Because 90% is almost all the way on, right? That's when you can start using it. So it's a good thing to know. Also controls. Rise time is super important. But you can extract that. Right.
some number tau times
Yeah, maybe.
some logarithm minus another number
Maybe.
times tau times another logarithm.
But the really helpful thing though is controls. It gives you stuff about stability, and I highly recommend for taking electives control systems. Genuinely, it is the most helpful elective that you can take. It's with Dr. XIE. You pronounce it Shia, I think. I have a hard time pronouncing it. It really should be a required class for the degree.
What is it offer?
It used to be offered, no, it's offered in the fall. But you have to take circuits 2 to take it. So it'll be in a second, but highly recommend. She's also lovely.
That last one, not even close to 0. EF2 was 0.
Exactly. And I was about to solve it. And then there's source of additional practice problems. So unfortunately, I can't.
Sorry.
No, you're good. I can't give out practice problems because he can reuse stuff. So I can't give all of the bank of problems I have, unfortunately. Like I said, I would ask him to send out the next problem set so that you at least have practice problems on the ones you haven't had homeworks for. Also, you can watch my old reviews. I have in this Teams and in the Teams HKN. There are hours of me blabbering, and I've reused some of the same problems, so you can probably skip over those. But There's a lot of doing brushes. But I'll show you really quick how to do this in the calculator. So do we remember how to do solve, menu, 3, algebra, solve? Write down a little solve. So we're going to literally write 0 is equal to negative 4.95 plus 6.75 times e to the negative 5t or something, no, t over 133.65 and 6. And then at the end, and make sure you go all the way over, you're going to do comma the variable you want to solve for. So comma t. We get that the time when it equals 0 is 41.45 microseconds. That make sense? Sweet. Okay. So P1 equal to 40. Okay. Cool. Do we have any other questions? We've been here a while.
For midterm 1. Like previous semester, you never did them back.
No, he gives them back. It's just sometimes, do y'all have your grades?
Yeah.
Oh, you can totally ask the TA, and he should be able to give them back. Yeah, I would see, oh, maybe see if you can get them on Monday. Kind of close to the exam. Yeah. But if the grades are graded, you should be able to get them. Okay, anything else?
Oh, I like.
Okay.
I think during one of the previous calculations, I
Did I
think,
do it wrong?
no, I think I might have done it wrong. Because I think I typed the same thing you did.
Negative 1.8.
Okay, that's fine. Thank you.
You're good. Okay, let's stop the recording.